Alright, now today's plan is to discuss some model questions targeting the term test, which will be starting tomorrow for most of the students. Right, this is the question from previous year's paper. I mean, your senior batches, immediate senior batches paper. If you can see here, this is the first term examination, grade 12, 2021. Right, since most of you are doing FWC paper, I thought of just discussing this, but don't expect this same question to you can't expect the same question in your paper. Don't do that. Don't by heart this, just getting an idea. So this question is you can see a velocity time graph is given to us, so probably this question will help us cover certain aspects in that area. A time at times t equals 0 from a particular point above the horizontal surface, a basketball is thrown vertically downwards vertically at a certain velocity. So you can see it starts, the graph starts at -4. Hope you can see that graph starts at -4. Graph starts at -4 and it goes to -10, and you can see it has taken how many seconds? 0.6 seconds. 0.6 seconds, and then suddenly it goes to +8. Here it's +8. Right. You have to visualize this. You should visualize this, then only it will be easy for you to do this question, right? During the time period of t equal 0 to t equal to 1.4 seconds, 1.4 seconds, that is this point. This time is 1.4 seconds, right? Okay. .4 seconds, right? The motion of the ball is shown in the velocity time graph. What am I doing? I'll put it this way: 1.4 seconds. Right. Consider that when the ball collides with the surface, it recoils back upwards within a time period that can be neglected. Ignore air resistance. So the change in time when its direction of velocity change, it's very small comparatively. So we are just taking it. It happened spontaneously at 0.6 seconds. So if you consider this scenario, if you put this into a diagram, this is what's happening, people. See if you can understand. Initially the ball is thrown, not dropped from a height. See, at time equals 0 from a particular point above the horizon, a basketball is thrown vertically down. So say a basketball player is just bouncing the ball on the surface. You all must have seen basketball, netball and stuff, no? Right. So downwards, initial velocity is 4 meters per second. 4 meters per second. And we all know due to gravity the ball will go down, and when it reaches the ground it has a velocity of how much? 10 meters per second. 10 meters per second. So this is happening in the time period when time is equal to 0, the object is here, and when time is equal to 0.6 second, it is here, right? And then suddenly it changes the direction upwards. What is the upwards? At what velocity is it recoiling? At what velocity is it recoiling? Hurry up. At what velocity is it recoiling? Quickly, let me interpret from the graph. At what velocity is it recoiling? Hurry up, hurry up, hurry up. It starts at 4 meters per second, it reaches at 10, and then at what velocity it's recoiling? It's 8 meters per second. Here 8, suddenly it goes to 8. Now 4 is taken as minus, 10 is also taken as minus, 8 is taken as plus. Why is that? Because 4 and 10 are downwards, 8 is upwards. That's why it goes to 8, and then its velocity becomes 0, but surely it will not reach the maximum height. No, it will not reach the maximum height. Its velocity becomes 0, and at that time is equal to what? Time is equal to 1.4 seconds total time in the stopwatch. So how am I surely saying that the object did not reach the maximum height? How do I know that? How do I know that the object did not reach the same height? Not the maximum height, same height. How do I know that the object didn't reach the same height? Anyone? How do I know that the object didn't reach the same height? This is the initial height from where the object was dropped, and this is the new height the object reaches. That's because when it reaches the ground, it is guys, come on, respond. When it reaches the ground, it reaches at 10 meters per second, but when it recoils, it recoils at 8 meters per second. So there is a difference in velocity. There is an energy loss here. correct? There's an energy loss, there's a loss in energy in kinetic, there's a loss in kinetic energy here. It comes at 10. If it had bounced back at 10, it would have reached the maximum same height once again. It would have reached the same height once again, but it is not. See, this is the initial level, but it is not returning at the same velocity, so there is an energy loss. So final potential energy will not be equal to the initial potential energy. You have to be careful. From what height was this basketball thrown? Right, how do I answer that question? From what height was the basketball thrown? Number one, guys, tell me what is, now they are asking for h1, right? H1, they are asking what is h1. See the diagram, which one is h1? H1 is this. Do you agree with me? This is our h1. This area is our h1, because we know in velocity time graph the area of the curve gives you the displacement. Can someone tell me what is this height then? What is this? Can someone tell me what this is? The area of this triangle. What is this? This is definitely going to be h2. That's going to be h2 displacement. Exactly, yes. Right? 4 meters per second to 8 meters per second is h1. 8 meters per second to 0 is h2, the area. So you can find the area of the curve to find the h1. Yeah, to answer the first part. From what height was this basketball thrown? h1. So h1 is equal to area of the curve, area under VT graph. I'll just put it that way, area under VT graph. So area, it's going to be half times, it's a trapezium, you see, it's a trapezium, half times what? Addition of parallel sides, that is going to be 4 plus 10 multiplied by 4 plus 10 multiplied by the time taken is 0.6. So the answer will be 0.2, 0.3, 14, 4.2 meters. I'm getting 4.2 meters. Vishma? 4.2, right? Because 4 plus 10, no? 4 plus 10 is 14, 14 into 0.3. Careful. So you can't make small mistakes like that. It will be really costly for you when you do the exams. Right, Roman 2. After the first time ball hits surface, what is the change in velocity with direction? Ooh, that's interesting. What is after the first time ball hits surface, what is the change in velocity with direction? Okay, can someone tell me the answer for that? Change in velocity. Change in velocity, people. Change in velocity is going to be equal to, this is where the vector addition is tested. No? So never mind, I will put it final velocity minus initial velocity. Let's put that in equation as well. Final velocity minus initial velocity. Right. What is the final velocity? Final velocity is 8 upwards. Correct? Yeah. 8 upwards. It is bouncing back at 8. Initial velocity, people, minus 10 downwards. Minus 10 downwards. And we have learnt under vector addition, when you get two vectors like this, if they are in opposite directions, what should we do? First, we have to convert both to the same direction. Therefore, 8 upwards plus 10 upwards. No? You can't say 8 minus 10 minus 2, because the directions are different. When the directions are different, you can't add them or subtract them. You have to change the directions to same, and then finally, it's going to be 18 meters per second upwards. Got it? 18 meters per second upwards. This is the answer for the change in velocity. So we are done with 1 and 2. Roman 3. After the first time ball hits surface, to which height would the ball have risen back up? So they are asking for h2 this time, yeah? h2, right? Quickly tell me what is h2? h2 is also area under VT curve. This time it is a triangle, right? It's a triangle, so it's going to be half into base is how much, people? 0.8 into height 8. It's 3.2 meters, I think. 3.2 meters. 3.2 meters. Simple. So far all good. 3.2, 4.2 meters, 3.2 meters. Right, so basketball is thrown from a height 4.2 meters it's very tall, it's taller than a floor. Yeah, so someone is throwing from top to game. In the gym they are just playing around. Fine, this is how it is. So third question is also done. These right signs were not necessary. Okay, fine. So we are done with 3. At what time would the ball have hit the surface for the second time? Ah, right, interesting. So how long will it take for the ball to come back to the bottom, people? How long will it take for the ball to come back to the bottom? Anyone? How long will it take? Any guesses? How long will it take for the ball to come back down? This is now this is positive and everything. Yeah. How long will it take for the ball to come back down? It will take another 0.8 seconds. Do you agree with me? Very good, Rishma, correct. Good. It will take another 0.8 seconds, people. It will take another 0.8 seconds for the ball to come back down, and when it comes back down, what will be its velocity? What do you think will be its velocity? Its velocity will be again 8. In a way, there is no air resistance. So it started at 8, goes up, becomes 0 and comes back here 8. And when it comes back, the time will be I have to add another 0.8 seconds to this, because from here to here it took 0.8 seconds. So from here to here it will take another 0.8 seconds, 2.2 seconds. 2.2 seconds. I think we might have to draw the remainder of the graph as well. So I'll continue that with this color. Wait. It will go up to 2.2 seconds. I'm sorry about this mess. Yes, this is how the graph will continue. Don't know whether they have asked us to continue the graph. Let's see. See, okay, now perfect. You can use this as the guide also. Nice. The graph will go up to that point and stop. Why? Because it has now again reached the ground when the velocity is 2.2. Yeah, the velocity is 2.2 seconds. Not the velocity is 2.2. The total time is 2.2 seconds. The velocity at which it hits the ground, once again, it's going to be -8. The reason for -8 is it will be going down when it is ready to hit the ground once again. This value is -8, right? So you have to say fourth one. The ball will take another 0.8 seconds. 0.8 seconds to hit the surface. We'll write that and say, so total time is how much? So total time 2.2 seconds. I will write both the answers to be on the safe side, no? Because we don't know which one they're expecting. At what time would the ball have hit? Maybe they are asking for the time on the x-axis. So let's just go ahead with this. And this time is 2.2 seconds. 2.2. I hope you all understood it, because there is no air resistance. So time taken to go up and time taken to come down will be same. If you go up at 8, you will come down at 8, and then it will hit the surface, and what will happen to that velocity at which it bounces back? Any guesses? What do you think will happen to a velocity at which it bounces back? That will be less than 8, correct? It will go up with the velocity v. After again there is going to be energy loss. So definitely 8 will be the larger number. And I hope you understood, because it came down at 10, but when it goes up at 8. Then again it comes down at 8, because here there is no energy loss. And then but when it bounces back, it will not bounce back at 8 itself. There will be a change in velocity, right? At each instance the ball hits the surface, the ratio of speed hitting the ground over speed from the ground. I think there's a printing mistake here. Speed hitting the ground over speed from the ground. Yeah, should be speed from the ground, I think, because so yeah, that is the ratio they're talking about, from the ground. Speed hitting the ground is 10, speed from the ground is 8. Speed hitting the ground is 8, speed from the ground is v, we don't know, right? At each instance the ball hits the surface, the ratio of speed hitting the ground over speed from the ground is a constant. What is the speed at which the ball recoils from the second time of the ground? I just took it as v, they are asking for v. Okay, So to answer that part, Roman 5, what do you think we should be doing? Right, so we have to say speed at which it hitting the ground, hitting over speed at which it recoils. So speed recoiling. Is that clear, everyone? Speed at which it hits the ground and speed at which it recoils. So speed at which it hits the ground, how much is that? That is 10. First, for the first time, right? Good, Rishma, correct, good. And speed at which it recoils is 8. That is the first time it bounces. The second time it bounces, it hits the ground at 8 and it will recoil at a velocity of v. We don't know what that velocity is. So we can say v goes up, v 8 into 8 over 10, 8 into 8 is 64, over 10 is 6.4 meters per second. 6.4 meters per second. Okay, right, so that is it. That is how you find it. So every instruction is clearly given to you, and if you want, you can continue the graph further. How? You can draw it further up like this until 6.4. Until 6.4. Where is that? This is 6, somewhere here, 6.4. Not bad. That is that value. So I'll just mark it for the sake of marking. I don't know whether they have asked to continue it in the next part, but plus 6.4 is the value. Copy the above graph onto your answer sheet and complete the velocity time graph for the motion of the ball till t equal 2.5 seconds. My god, right, okay. So I have completed up to 2.2 seconds. I have completed up to 2.2 seconds. And how do I complete up to 2.5 seconds? All I have to do is draw a parallel line to this. So it will be like somewhere here. Yeah, somewhere here. It should be parallel. And can someone tell me the final velocity here? What will be the final velocity? Now 6.4 is where we starting now with 6.4. In 0.3 seconds, by how much will the velocity of the object reduce? 6.4, within 0.3 seconds the velocity will reduce by 3, because each 0.1 second velocity will reduce by 1. Do you see that? See now, here 0.6 to 1.4, it's falling under gravity, na people. So gravity is 10 ms minus 2. From 0.6 to 1.4, there is 0.8 second, the velocity changed by 8 meters per second. So here from 2.2 to 2.5, the time duration is 0.3 seconds. So in 0.3 seconds, the velocity will change by 3 meters per second. So final velocity of the object is going to be 3.4. 1, 2, 3, 3 and 3.4, almost 3.5, somewhere here. Right, that is where it's going to be. So I thought we might have to stop after 2.2, but it doesn't seem like that. They're expecting us to draw until 2.5. So this is how that graph is going to look like. So I hope this is clear to everyone. A very good question about motion under gravity and how to analyze VT graph and all those things. Right. So I did everything here. I know it's a bit congested here, but I wanted to do everything there itself so that you will have everything with you in the answer. All right. Yeah, it's a good question. Good. So I hope you got an idea from this. Yep. Rishma, have you tried this paper before? No. No. Okay. Right. Fine. So while I was explaining, you also did it. No. Good. Good. Right. Fine then. That's it. That's the first part for you. Now you also can try with me if you want. You also can try this question. Try while I'm doing, so that. Okay. Good. Now let's move on to the next one. There's another question. Second part. What is it? This is about projectile motion. Projectile motion is also very useful now, people. We have done so many questions. Did we try this part of the class? Tell me quickly. Yes or no? No, I can't remember doing this with you guys. No, right? No. Okay, super. So this is going to help us get an understanding about projectile motion, which is another integral part of mechanics. Right, so let me prepare the screen for you. And the reason why I have made why I'm writing by making the letter small is this: if you have all the questions at one place, then only it's easier for us, because essay questions are continuation of people. So if you don't know the answer for Roman 1, you might not know the answer for Roman 2. So that's why I'm doing it here. I hope the question is readable. Can I get a thumbs up from you if you can, if you are satisfied, if you can manage with the font size? Right, okay, super, good. So everyone, please pay attention. Let's get started. The figure 2 shows the instance where a basketball player hits the ball. The ball leaves the hand of the player at speed u at an angle theta from the horizontal. The height of this point from the ground is simple h. You can see that, yes. The height of the basket from the ground is capital H, alright. The horizontal distance between the player and the basket is simple d, right. So the actual height the basketball reached, it is neither simple h nor capital H, it is this difference between those heights. Do you agree with me? It's neither simple H nor capital H. So what is the height? What's the height difference? He started at simple h height from the ground. The ball starts at simple h height from the ground, and the ball reaches to a total height of capital H from the ground. Therefore, the displacement of the ball is in fact how much? It is going to be capital H minus simple h. Do you all agree with me? Capital H minus simple h. That is going to be the displacement of the ball upwards. Upward displacement of the ball, and since this d is the horizontal displacement of the ball. Let's take the ball started here at time equal to 0, and the ball reaches here where the basket, in fact, when time is equal to t, and it starts at velocity u. So we all know it's regular custom. The vertical component is going to be u sine theta, whereas the horizontal component is going to be u cos theta. If I mark everything like this, it's easier for me. Good. And it reaches the the basket. When it reaches the basket, people, what about its velocities? Now I will erase this part of the basket because I need to mark the velocities and stuff. Right, only the basket is enough. Right, when it reaches the basket, the ball, in case if you need, the horizontal component will not change, isn't it? It will remain as u cos theta. We don't know. No, it will not change. It will not change. But the vertical component, it's going to change. The vertical component is going to become a new velocity v. We don't know what that is, right? But horizontal component will not change. Okay, all right, all okay. Done. Give the flight duration of the ball capital T. Oh, this is capital, given as capital T, no? Flight duration, not simple T. It's given as capital T. Here, when it comes reaches here, time is capital T. I have put the vertical component downwards because the ball will be now going down. See, it has reached the maximum height and it will be going down. At the maximum height, what about the maximum height? At the maximum height, the vertical component is 0, right? Vertical component is 0, but the horizontal component will still remain as u cos theta. It will not change. That's important. Projectile motion, u cos theta, right? Give the flight duration of the ball capital T in terms of d, u and theta. I think that is simple because you can use the horizontal. First of all, you can use the equation horizontal, s equal ut plus half at square. And don't forget someone, the gravity is there. I mean, downwards acceleration is equal to g, horizontally acceleration is equal to 0. Okay, so when you say s equal ut plus half a squared horizontally, we have d, that's a horizontal displacement. Horizontal initial velocity is u cos theta, total time taken is capital T. What is acceleration, people? Horizontal acceleration? 0. You can't put g there, careful, it's 0 because only the vertical one is g, horizontal one is 0. Therefore, simple d is going to be equal to u cos theta capital T. U cos theta capital T. So capital T is what we are supposed to find out. Therefore, we will directly write capital T capital T is going to be equal to d over u cos theta, d over u cos theta. Show that capital H is equal to simple H plus d tan theta minus some big answer using the conclusion derived in part 1 and the vertical motion of the ball. So, they are indirectly saying apply the equation for apply the same equation vertically. Vertical displacement is equal to ut plus half at squared. Okay, now what is the vertical displacement? I have clearly marked that in the diagram. So, yeah, since I have marked that in the diagram, I can use these things. Now, you also better draw a rough diagram. You don't have to draw the man and all, the ball, it's enough. The path of the ball in your answer script and mark these things, that's enough. So, the vertical height is capital H minus simple h. What is the vertical initial velocity? U sin theta, and time taken is d over u cos theta, plus half into, for g you have to put what? So, for a you have to put minus g. For a you have to put minus g. If you put g, it's wrong because the direction must be taken into consideration, and time, for time I will put capital T square, that is d over cos theta square. Alright, so here you can see u can be cancelled out. There's this u and this u can be cancelled out. Other than that, we can't cancel anything. I will be getting capital H minus simple h. Capital H, yeah, capital H equal minus simple h equal to sin theta over cos theta d is d tan theta minus gd squared, same answer, na? Gd squared by 2 cos square theta, 2 u square. Where did u squared come? Oh yes, I forgot the u in the time. I forgot the u in the time. God, yeah, there must be a u in our timing, people. Sorry about that. There should be a u in our timing. U. Right, this. So, u squared cos square theta. Yes, so that is the answer they are expecting us to figure out. So, capital H, if I make that the subject, simple h goes to the right side, becomes h plus d tan theta minus gd squared over u squared cos square theta. When you look at that at once, it might look really intimidating, but if you stick to basics, getting that answer is not difficult. Okay. Roman 3. Besides, if you just now see the advantage of when them asking us to show an equation is, even if you make mistakes, you can figure it out. I have missed the half also. Half is then half into u squared cos square theta. Right, done. Find the value of capital H if u is 10. Every number is given to you. Even cos 45 and tan 45 given. It's not always done, so don't rely on that value. They will not give it all the time. In the final paper, I have never seen them giving the paper, number. Never seen this in the sense. If it was a number like cos 35 or something, they will give, but cos 45 and all, they don't give. So, don't get complacent. Remember, you should remember these values. They have given every letter and they are asking you to find capital H. Everything is given to you. So, let us start. Capital H is equal to, I am not going to rewrite it because I have already written it. Simple H is 2 plus D is how much? 8 tan into tan 45. Tan 45 minus G is 10 into d square is 8 squared over 2 into u 10 squared, good, and cos theta squared, that is cos 45 squared. Good. So, here we have h equal to 2 plus 8 into 1 minus one of the 10s can be cancelled out. I have a 10 here and 10 squared here, and this 2 and 8 squared, 2 and 8 squared, it's 32, and so you have 32 over half, is it? 32 over half. I am getting a big number. And there's a 10 at the bottom. Sorry, there's a 10 at the bottom. It's in fact 3.2 over half. No, 3.2 over half, because I can't get a negative value for capital H, people. There's a 10 at the bottom. Don't forget that. So 32 over 10 is 3.2 over half. Finally, we will be getting capital H equal to 2 plus 8 is 10, 10 minus 6.4. This 2 will go up, become 6.4, 3.6 meters is the answer. Please don't ask me how it came. You can do your own math and get that answer, right? 2 plus 8 is 10. Here 8 square is the 64. 2 is there. So 2 and 32. 2 and 64 is 32. 10, one of the 10s here. One of the 10 and one of the 10s here will get cancelled off. 32. Okay, fine. This is the answer. 8 minus, sorry, 10 minus 6.4. Good. Roman 4. In part B3, find the highest height, capital H naught, from the ground attained by the ball. Oh, I think we have done so many such questions in our class. Can you remember? I think at the class we have done all these type of questions. They are asking for this capital H naught. Correct? How do you find that? Very interesting. How do you find that? I think we can't directly find capital H naught from the ground. Means I think I should draw it this way because it's drawn in 3D. If I might have to extend this line. Where, which line? That is this line. This is the ground level, right? From that ground level, you can't find capital H naught directly. Instead, I think you can find out simple H naught, which is this particular height. This particular height, we'll take it as simple H naught, and then if you find simple H naught, it's a matter of adding simple H to find capital H naught. But read the question carefully. Find the highest height from the ground. Highest height H naught from the ground. Okay. Can we use the equation to find maximum height? You can't. You can't do that. It's an essay question. Now you might have you might be able to remember the equation H is equal to u squared sine squared theta over 2g or something like that, right? You can't use that here. You have to show the work. So let's consider this point to be capital A, the point where the object is starting, and the basket to be capital B, okay, and the maximum height point as capital C. This is capital C, right? A, B, C. Then let me apply the equation from A to C vertically upwards. What equation do you think we should be applying? Vertically upwards, B squared equals U squared plus 2AS, but from A to C. Okay. Final velocity, final vertical component of velocity is 0 at C. No argument that. Initial velocity is sorry, u sine theta squared, u sine theta whole thing squared, plus 2 into, for A I have to put minus g, into, for S I have to put H naught, simple H naught. I have clearly indicated that in the diagram, simple H naught. So 0 equals u is 10, sine theta is 1 over root 2, because it's sine 45, no? Theta is 45 squared, minus 20 H naught, and that will be this 20 H naught goes to left side, 20 H naught, that is equal to 10 over root 2 square, that is 50, is it people? 50, because 10 square is 100, root 2 square is 2, and that is 50. So H naught is going to be equal to 50 over 20, 2.5 meters. 2.5 meters. Understood? Okay. Roman 4. I hope that's clear. But that's not the final answer. Oh, that's not the final answer. Final answer should be what, people? Tell me what's the final answer. So capital H naught, we know capital H naught is equal to simple H naught plus H, and that is 2.5 plus simple H was given somewhere 2. Yeah, 2 answer is 4.5 meters. That is going to be the final answer. 4.5 meters. Clear? Right. And then Roman 5. So what happened to that cos theta in the second question, first step? Second question, first step. It became tan theta, Abdullah. Sin theta or cos theta is tan theta, no? Haven't we studied that? Sin theta over cos theta is equal to tan theta. Don't you know that? You know, right? But you are not doing maths. That's the problem. Yeah, okay, right. This is what happened at this point. And then Roman 5, what does it say? Right, I hope we have enough space to finish it. Compare the values obtained from B3 and B4 above with H dash. The height from ground at which the ball hits the point the hoop is attached, and the highest height attained by H naught. Right, H dash is the now for capital H and capital H naught we have found the initial values. They are asking us to compare another value for capital H and another value for H naught. No? Calculations are not necessary. Inequality relation is expected. So there are two situations they are expecting us to decide. When a ball of twice the mass is thrown with initial velocity 10 meters per second, theta 45 degrees Celsius, 45 degrees. Roman 5 first one. Okay. So initially they are throwing at theta is 45, I think. Theta is 45, no? Initially theta is 45 initially, and u is 10 initially, according to the information given here. So now they are throwing at the same initial velocity, same angle, but they are increasing the mass of the ball by twice. What will happen? What will happen? Tell you. Will H naught and capital H change? When they throw another ball of double the mass of the initial ball at the same speed and same angle, the new height is H dash, this height, and new maximum height is H naught dash. What will happen? Will they change? They will not change. They will not change. You know why? In the question, they have clearly mentioned us to ignore the air resistance. Where have they? They have not mentioned anything. No? Have they mentioned? I thought in the previous question they had mentioned, but in this one they haven't mentioned. So what are we going to do? Calculations are not necessary. Have they mentioned anywhere, people? This is going to be a very tricky question. No, we have to ignore air resistance anyway. We have done all these questions ignoring the air resistance, people. I have taken simple g for acceleration, and I have taken horizontal acceleration 0. That means what have I done? Tell me. I have obviously ignored air resistance and only done this question. They are asking us to find out mass is mentioned. That's okay. If mass mentioned doesn't make a difference, Amjad, because they are asking us to derive this equation. The only way you can derive this equation is by ignoring air resistance. Here we have not considered air resistance anywhere. No? So these equations we have not considered air resistance anywhere. So H dash and I mean this is the answer. Capital H dash, that is the new height, that will be equal to initial H, and in new maximum height from the ground is equal to the old maximum height from the ground. I will write the reason also, because there is no air resistance. There is no air resistance. Hence if theta and u are same, heights will not change. Heights will not change. Heights will not change. By using conservation, no, Amjad. Even when you use conservation of energy, m will get cancelled off, Amjad. Half mv squared equal to mgh. M will get cancelled off, even if you use conservation of energy. Do you agree with me? You have to put half mu squared, half mv squared, and this thing. What do you call that? Height. Okay, since Amjad brought it up, let's see energy. Conservation of energy. Conservation of energy. From where to where? Where to where do you want to put? Okay, fine. Let's try to find capital H naught. If you want to find capital H naught, I have to apply it from A to B. So at A, the object has what? At A, the object has, okay, never mind, gravitational potential energy at A, and at A, the object has kinetic energy as well, and at B, the object will have gravitational potential energy and kinetic energy too. For example, since but I can't add anything else because we have ignored air resistance. Gravitational potential energy at A is mgh. Kinetic energy at A is half mu squared. Okay, gravitational potential energy at B is mgh naught. Kinetic energy at B is half m u cos theta squared. So what is happening to m, people? Tell me what is happening to m. All these m's will get cancelled out, even if you put conservation of energy. Gone, 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 gone. So capital H naught does not depend on mass. Amjad, clear? Hello? Amjad, are you there? Right, he is missing. I hope others understood. Even if you want to prove that with energy, conservation of energy, you cannot prove it because mass is getting cancelled off. So it doesn't depend on mass. It will be convenient. What do you mean convenient? 2m and m. You know, 2m. If you put 2m also, it will get cancelled off. If you put m also, it's going to get cancelled off. Okay, okay. You are saying that way. Okay, okay. But yeah, okay. But just remember, whether it's m or 2m, the values don't change. The acceleration and all those things. Right. Next one. V 5 5 2. Okay, people. Next one. Roman 5 second one. Now what are they doing? Roman 5 second one, what they are doing is they are not changing the velocity, but they are changing the angle. They are changing the angle. What do you think will happen? Initially they threw at 45 degrees. So when you throw at a higher angle, the initial velocity is same, don't forget that. So they are throwing at 10 meters per second and initially 45. So what will happen? The path, it will be like this, right? But this is 45, remember, this is 45 degrees. And on the other hand, if you throw the ball at 35, throw the ball at 35, what's going to happen? It's going to take a lower trajectory. Do you agree with me? It's going to take a lower trajectory. You can even, because we have learned 45 gives you the maximum what? 45 gives you the maximum height. That's one point. On the other hand, anyways, you can, clearly understand the heights are going to be different. No? This way. When you throw at 45 and when you throw at 35 with the same initial velocity, this is definitely going to happen. So what can I say about capital H and H dash? Definitely H dash and H will be less than their previous values. Okay, they will be definitely less because the angle is less. So when the angle is lower, they will go somewhere here down and it will go below the basket. From B3, okay, show the variation of vertical velocity component of ball with time. Value is not necessary. From B3, show the variation of vertical velocity. B3, wait, what is B3? Okay, show the variation of vertical velocity component of ball with time. Values are not necessary. So what kind of answers are we going to get here? Which is 6. Vertical velocity. So what kind of graph can we expect, people? Initially, v cos theta, sorry, v in meters per, no, we don't have to put the value. So it's just a graph would be enough, v and time. What kind of graph do we get? At the beginning, see, it's vertically upwards, u sine theta, and it becomes 0, and then it turns to downwards. Hence, I think the graph is going to be something like this. Agreed? Because upward means it's taken plus, it should be taken as plus. So this u sine theta, if you take this as plus, then v should be taken as minus because it's downwards now. Okay, so you don't have to mark the values, but just for sake of marking, let's say this is plus u sine theta here, and this is minus v. Okay. Right, next questions. Question 2 essay. First one, define momentum and impulse. Momentum and impulse. So, what is momentum, people? Momentum, we normally say momentum is equal to mass into velocity, right? The equational form is mass into velocity, or else you can also say what? Difficulty in stopping a moving object. No? Difficulty in stopping a moving object. Write both. You're on the safe side. And what is impulse? What is impulse? Impulse is simple. Impulse is equal to change in momentum. That's all. I prefer this answer than force into time. It's not always force into time, it's the impulsive force into time. So, safest answer is going to be change in momentum. That is impulse. Give the principle of momentum. Now, this is something you will have to know in essay questions. They normally ask for these principles. So, you have Newton's laws 1, 2, 3. You have moment principle. You have moment principle. You have principle of momentum 5. So far, we have learned 5, right? I don't think we have, and the parallelogram theorem. What is parallelogram theorem? They might ask you to write those things. So please write them and practice them. I don't want you to by heart it word by word. I want you to understand the key aspects of it and put that in your own words, right? Practice it before you go to the exam. There are 6. I don't know which. They have asked about momentum. The principle of momentum is when the resultant force acting on a system is 0. That condition is important. The resultant force acting on a system is 0, total linear momentum will be conserved. Total linear momentum in the system will be conserved. You have to, you can't say initial momentum equal to final momentum. Like you can't write a blunt answer like that. It has to be very precise. So you have to give the condition. That's done. So we are done with Roman 1. Oh no, this is not Roman 2 rather. This is Roman 1. What? Right. Oh no, that's Roman 2. Sorry. Roman 2. Correct. Next part, the air-filled balloon in figure A floats in air at rest. Explain what happens to balloon in figure B if the neck of the balloon is open compared to the balloon in figure A. What will happen? Right, what will happen, people? It's like, when you are a small kid and all, you might have done this. In birthday parties and all, it happens. What happens? When you open the neck, what happens? When the neck is opened, Newton's third law. Now open, air rushes out of the balloon. Air rushes out of the balloon. Air rushes out of the balloon. Rushes out of the balloon. And it presses the air, atmospheric. It presses the atmospheric air. It presses the atmospheric air below the balloon downwards. Atmospheric air below the balloon downwards. According to Newton's third law, what happens? According to Newton's third law, atmospheric air gives an equal and opposite force where atmospheric air gives an equal force. Atmospheric air, I will give it this way, not gives, exerts an equal force to the balloon in the upward direction. correct? So what happens to the balloon? Balloon goes up. Even a small kid will say, what happens when you open it up? The balloon will go up, no people? Due to R. There will be no R, Amjad, here. There will be no R. There will be no R here. For R to be there, it should be in contact with the surface now. When it is floating in air, it will have something called upthrust. Here it will have upthrust, not this thing, not R. For it to have R, it should be on a, it should be on a table or some surface. So here what's happening is, it will have a weight, and that weight is actually balanced by upthrust. It's in air, we haven't learned upthrust yet, but in O level I hope you have heard of upthrust, right? So here weight is balanced by upthrust, not perpendicular reaction. For perpendicular reaction to happen, the balloon must be in contact with the surface. It's floating in air. Here what happens is, weight is there, no, right, up, but upwards how many forces will be there now? Upwards there will be two forces now. Upwards now there will be upthrust, and at the same time thrust force by air, not lift force by air, lift force, both will be acting. And how did the balloon get the lift force? That is because the atmospheric air at the bottom is pushing it upwards. Amjad, okay, did it clarify it out? You wanted me to here, Amjad wanted me to draw a free body diagram and show how it's happening. It is not because of capital R, in the sense the capital R we learned, it is because of lift force it gets as the atmospheric air pushes it up. So earlier weight is equal to upthrust. We will learn about upthrust and all later. There's an equation for upthrust, not now. We'll be studying about that very soon. Here there's an additional force created by air. I mean the atmospheric air below the balloon, the air which ejects out of the balloon is pushing that air downwards, the air which was here, atmospheric air. So atmospheric air will push the balloon upwards, and that is that lift force. Because of that lift force, the balloon will go up. I hope everyone is convinced. Everyone is convinced that when you open the neck of the balloon is going to go up. Why is it happening? This is what's happening. Done. That is how a rocket goes up. That is how a rocket goes up. Okay. Done. Now let's move on to the next one. Part B. Part B, right. So let's finish part B separately. I see there's a part C also. Let's first of all focus on part B now and finish it off. A space probe of mass 100 kilograms is attached to a spaceship of mass 5,900 kilograms. 5,900 kilograms. Standing at the launching pad. Right, you know what a launching pad is? Rockets and all, they are launched. The upward thrust needed to move the spaceship is 9 into 10 to the power 4 newtons, which is achieved by burning 12 grams per second of fuel per second and expelling the hot gas thus produced through the nozzle at the bottom. Like exactly like how balloon went up when you open the neck of the balloon at the bottom, the same thing is happening. Because what's going to happen now? Hot air is going to be released out. So that hot air, what will it do? Hot air will push the air downwards. Atmospheric air. Therefore, according to Newton's third law, atmospheric air will give a upward force to the rocket. So rocket will go up. That's what's happening. Force of upward thrust is given by the product of rate at which fuel is burned and exhaust velocity of the gas relative to shuttle. So this is an important equation. They have given that already here. The force of upward thrust is given by the product of rate at which fuel is burned and the exhaust velocity of the gas relative to shuttle. So if I put that into an equation, upward thrust that is equal to product of rate at which fuel is burned. So rate at which fuel is burned burnt multiplied by exhaust velocity. Oh wait, sorry. Wait a minute, people. Sorry. Upward thrust, that is equal to rate at which fuel is burnt. Remember this equation, multiplied by exhaust velocity. Have they given the rate at which the fuel is burnt? Anyone? Have they given the rate at which fuel is burnt? Have they given or not? You see a number. Rate at which fuel is burnt multiplied by exhaust velocity. Yes, I see a number here. Burning 12 kilograms per second of fuel per second. I mean, per second was not needed really. It's already given. Yeah. This is the rate of burning. Understand? Fuel for 12 kilograms per second. They have not given the velocity. That's okay. Okay, well, let's get focus now. Right, now, Roman 1. What is the initial acceleration when the spaceship starts to move from the launching pad? Right, now let's think of the spaceship. Spaceship is like this. And what are the forces acting on the spaceship, tell you? How many forces acting on the spaceship? Hurry up. Space probe, okay, right. A space probe of 100 kilogram mass is attached to a spaceship of 5,900 kilograms. So there will be a weight, right? W is equal to mg, and an upward force is provided, that is F, and the acceleration they are asking us to find out, A. Then you can apply upwards, F equal ma. So it is F minus mg equals ma. Upward force is 9 into 10 to the power 4 minus, what is the mass, people? What is the mass? For mass we have to put 6000 into 10. Agreed? Because the total mass is 100 plus 5, total mass 100 plus 5900. So that is 6000 kilogram. And m, it's again 6000 into acceleration A. So 9 into 10 to the power 4, this is going to be 6 into 10 to the power 4. 9 into 10 to the power 4 minus 6 into 10 to the power 4 equal to 6 into 10 to the power 3 into A. So on the left side, it's going to be 3 into 10 to the power 4. If not, I'll write it, okay, 3 into 10 to the power 4, never mind, equal to 6 into 10 to the power 3 acceleration, into acceleration. Therefore, final answer for A, I will, instead of 3 into 10 to the power 4, I will write it as 30 into 10 to the power 3, correct? I can write it that way, over 6 into 10 to the power 3. I am getting an answer 5 ms minus 2. So I hope everyone got it, 5 ms minus 2. You need to figure out what is the upward force. Now, yeah, figuring out weight is important. Both are there, and we have to consider the probe as well as the spaceship. Roman 2. Find the velocity of the spaceship after 60 seconds of motion, considering that its acceleration is constant. How do we do that? Acceleration of the ship is 5. You can't put 10 now. You can't put 10. It's we have found it as 5. It's going up at 5 ms minus 2. So you should not bother about gravitational acceleration. We have considered gravity and everything and only got this answer. Now the ship has an acceleration of 5 ms minus 2. Anyone tell me the initial velocity? I think it was at rest, so it's 0. Final velocity we have to find out, and after 60 seconds. So what is the equation, people? What is the equation we should be using? Upwards, v equals u plus at. Very simple. V equal u plus at. Right. So what is going to be the answer? The answer is going to be v equals 0 plus 5 into 60, not 10. Careful, because it has an upward velocity of this of 5. Then v is equal to 300 meters per second. It has reached a velocity of 300 meters per second, right? Find the exhaust velocity of gas relative to spaceship. Good. How do you find that? For that only we have that equation. The equation I just wrote little while ago, people. What is it? Upward thrust. Upward thrust is equal to rate at which fuel burnt multiplied by exhaust velocity. exhaust velocity, right? What about upward thrust? Upward thrust, what is upward thrust, people? Upward thrust is this value. See, they have given, they have already given upward thrust. It's already provided in the question. Upward thrust is 9 into 10 to the power 4. So if I substitute it here, 9 into 10 to the power 4, what is the rate at which the fuel is burned, people? Rate at which the fuel is burned is 12 into exhaust velocity V. So it's very simple. Once again, all you need to do is figure out this thing in the question. So it's a 9 into 10 to the power 4 divided by 12. 9 into 10 to the power 4 divided by 12. 9 over 12 is 3 over 4, that is 0.75 into 10 to the power 4, and final answer 7500 ms minus 1. So it's a very high velocity. Air has to be exhausted at high velocity to create the required upward thrust. Right. After 60 seconds of motion, find the exhaust velocity of gas relative to Earth. Why is that happening? Relative to Earth, no? Okay, interesting. For that, we have to use this thing. What do you call that? Relative motion. Can you remember? We have learned relative motion, people. Relative motion. So we'll take find the after 60 seconds of motion, find the exhaust velocity of gas relative to Earth. So this is this value. Now Roman 3, what we found is this: find the exhaust velocity of gas relative to spaceship. No? So I will use capital G for this thing, gas. I hope you can remember. Rishma, did we do relative velocity? S for spaceship and E for Earth. Did we do relative velocity, people, at our class? Earth. Yeah, okay, we have done relative velocity, and I hope you guys can remember how to write those equations. The question is, what is the velocity of gas with respect to Earth? Okay, so that is going to be what is the velocity of gas with respect to spaceship minus what is the velocity of spaceship with respect to Earth. This is the equation. No? Wait a minute, it's going to be minus or plus or minus the plus the okay, it should be this way, no? Plus, man. Okay, sorry, it should be this way. Now normally this is how we wrote, now people. I think this is how I explained. Velocity of A with respect to B, we wrote it as velocity of A with respect to Earth minus velocity of B with respect to Earth. This is the equation we learned. Now the problem is, I have velocity of I have to find velocity of right. Now I know a few things. Wait, before I write the equation, I'm going to be very careful here. You have to be very cautious now. Now wait, I will write the other information here. Velocity of gas with respect to Earth is what we have to find out. Velocity of spaceship with respect to Earth, we know that. How much is that? After 30 seconds, it's going at 300 meters per second. Where? Upwards. Careful, huh? What is the velocity of gas with respect to spaceship? It is this value, 7500. But what is the direction, people? Downwards, no? With respect to spaceship, the gas will get exhausted out downwards. Gas should go down, then only spaceship will go up. So these are the three values, right? These are the three values. So it's like velocity of A with respect to B, velocity of A with respect to Earth, velocity of B with respect to Earth. So if I combine these three things, I can say best way of writing it is velocity of gas with respect to spaceship is equal to velocity of gas with respect to Earth minus velocity of spaceship with respect to Earth. That is the best way of writing it, because the equation we have learned for relative motion is velocity of A with respect to B, velocity of A with respect to Earth minus velocity of B with respect to Earth. I hope you guys understood this. So velocity of gas with respect to the spaceship is known to us, that is 7500, but downwards. Don't forget the direction. Velocity of gas with respect to earth is what we have to find out. Yeah. Minus velocity of spaceship with respect to earth is 300 but upwards. Okay, upwards. So this 300 goes to this side, 7500 downwards plus 300 upwards equal to velocity of gas with respect to earth. So finally velocity of gas with respect to earth, that is going to be 7500 downwards minus 300 downwards, and that is 7200 meters per second downwards. This is the answer. Careful. So you have to read the question carefully, identify the components and apply relative motion equation. Right. So always stick to the basics, don't try to change it. Now if you know this, use that, but when you use it the way exactly you used it before. So you have to identify the components carefully, and then normally they ask for this one, the one on the left side. They will give you these two. In this question they have given the one on the left side, they are asking for one of them on the right side. That's it, simple. Right. Roman 5. What is Roman 5? Roman 5. Explain this statement. Even when the upward thrust acting on the spaceship is constant, when the fuel burns, its acceleration increases. Okay. What is that? Why is that? Right. Now explaining Roman 5. What's the time now? Okay, almost 7. F equal ma na people. We can put F equal ma. No? F equal ma. Yes. F equal ma. Very good, very good. Khadija's answer is correct. F equal ma. Now they have said acceleration. No? Acceleration increase. So I'll make acceleration the subject. Acceleration is equal to force over mass. Force over mass. And in the question they have said F is constant. F constant. If F is constant, according to the question, you can say acceleration is inversely proportional to mass. Acceleration is inversely proportional to mass. Yes, exactly. What will happen when fuel burns? When fuel burns, what reduces? Mass reduces. No? When fuel burns, mass reduces. So when mass reduces, what will happen when mass reduces, people? Acceleration will increase. Acceleration will increase since acceleration is inversely proportional. Acceleration is inversely proportional to mass. You don't have to write the last part, but you should have explained in with the equation. Otherwise, you have to write it. It's better to write inversely proportional to mass. Remember, the spaceship will carry a lot of fuel in it. As the fuel keeps burning and burning, the mass of it is going to reduce. So acceleration will keep increasing. Draw the variation of velocity time graph according to the instance in B5. Okay, what is the instance in B5? Increasing acceleration. Can someone tell me what kind of graph we can expect there, people? Increasing acceleration graph. We have to draw a VT graph, but increasing acceleration, velocity time. This is the answer for 6, Roman 6. Anyone? Gradient increases, exactly. Acceleration is the gradient of VT graph. So if you want to plot a VT graph, it will look like this. Increasing gradient graph. This is the increasing gradient graph. Okay. What's the reason? I'll just put the reason as well here, because acceleration is the gradient of VT graph. That's enough. Okay. Acceleration is the gradient of VT graph. Therefore, it will have a shape like this. Remember these graphs. I think I mentioned when we were learning velocity time graphs, sometimes you might get questions where the acceleration is increasing. So it's not always a straight line. Sometimes you will get curves like this in VT graph. Normally we get graphs like this in ST graph. That's very normal. But if they have mentioned that the acceleration is increasing, then this is the kind of graph you should draw. Okay, people. Not bad. No, the first two questions were not very difficult. Answers were also not complicated. There's what simplifications and all was quite okay. It's all about you how much you are going to understand the question. That's where it all that is it will your success about the exam is going to revolve around that.